Okay, let's take a look at sample problem 4.5. We're now looking at reduction-oxidation reactions, or oxidation-reduction, redox reactions. So let me put this in the box here. That we're dealing with something called redox. This is the third type of reaction that we're going to look at. We looked at precipitation, and that's when we did the solubility guidelines and the molecular ionic and net ionic equations. Then we did acid-base, where we looked at the molecular ionic and net ionic equations for acid-base reactions. Now we're going to do reduction-oxidation redox. There's two different approaches that we're going to discuss in general chemistry for redox. The first is called the oxidation number approach. The oxidation number approach is the idea that you assign a number to each atom in a substance. And that number is called an oxidation number, okay? Or an oxidation state is another term that's used. So these are just numbers that we make up. But what we do is we try to base them, in some sense, based on electrical charges. So for example, we may know that sodium has a charge of +1. We would say its oxidation number is +1. Or we might say that an element doesn't have any electrical charge. Its charge is 0, so its oxidation number would be 0. Or an oxygen ion called the oxide ion. We would say, well, based on our experience, it has a charge of -2, so we would give it an oxidation number of -2. But what happens is, it turns out that if you use this approach, you end up with some interesting results that can be useful in giving us some insight into certain types of reactions. Redox chemistry is essentially the idea that one atom will transfer an electron to another atom. Okay, so I'll talk about that a little bit later. But for right now, let's just look at this sample problem. Determine the oxidation number of each atom in the following compounds and ions, and ion, because only one of them is an ion. So there's 4 of them here, A, B, C, D. There's SO2, NaH, CO3 2 negative, and then N2O5, all 4 of them. To do this, we use what are called the oxidation numbers. So table 4.5, elements with reliable oxidation numbers in compounds or polyatomic ions. You should have this table ready to use whenever you do these sorts of problems. And what this does is essentially tells you what the oxidation number is for several different substances. Not all of them, but several of them. Fluorine is -1 in a compound or polyatomic ion. Group 1 or group 2 metals, those are the alkali metals and the alkaline earth metals. Lithium, sodium, potassium, rubidium, cesium, beryllium, magnesium, calcium, strontium, barium. Those are either +1 or +2. Hydrogen +1. Oxygen -2. Group 7A, that would be chlorine, bromine, or iodine, -1. They give you some exceptions in there, and those exceptions can be important. Let's take a look, though. Here's what you're going to do. Use those numbers there to figure out the oxidation numbers. So notice some of the elements are not in there. For example, sulfur is nowhere in there. Carbon is nowhere in there. Nitrogen is nowhere in there. And the reason for that is you can figure them out from oxygen, hydrogen, or some of the other elements, sodium, for example. So let's go through. We're going to start with part A first. A is an easy one, SO2, sulfur dioxide. So all you do with this one is you say, okay, let's go up to the table here. Oxygen, -2. All right, so oxygen's -2. So one way to do this is, I'm going to use little circles, I guess, like this. Doo-doo, doo-doo, doo-doo. So you got a sulfur and 2 oxygens. Okay. The rule there says oxygen is -2. So this is -2, and this is -2. So now you ask yourself, okay, what about sulfur? There's no rule about sulfur, so what do? We come back and we say, okay, this is a compound. There's no charge here. If it's a compound, the charges have to add up to 0. It doesn't mean they're all going to be 0. Obviously, 0 + 0 + 0 adds up to 0. But what we mean is when you add them all up, they're going to be 0. So if you have a -2 and a -2, what does the positive have to be to cancel the -2 and the -2? Well, it's got to be +4, right? So that means the sulfur's got to be +4. And that would be the oxidation number for all 3 atoms in that substance. -2 for each oxygen and +4 for sulfur. So if someone said, what's the oxidation number of sulfur in SO2? You'd say +4. What's the oxidation number of oxygen in SO2? -2. Okay. Let's try B. B's a little tricky. B, they're giving you a little tricky one here, just to be feisty. So we're going to do the same thing, NaH. And then we come back, oh, let's go back here. Hey, there it is. Hydrogen's 1, +1, except here's the problem. The exception is any combination of group 1A or group 2A metal forms a hydride. It turns out there's this very interesting exotic type of form of hydrogen called a hydride. Normally hydrogen is +1, but in some cases it's -1. Very reactive substances. You can buy them from these chemistry companies, not for home use, but in the laboratory, and they're very reactive. They're called hydrides. So see how it says the examples, lithium hydride and calcium hydride? In that case, it's -1. So in the case of sodium, sodium is a group 1 metal. Group 1 metals are +1. And then if it's a +1, that means the hydride's got to be -1. So hydride's -1. Again, this is a compound. So the charges have to equal 0. +1 and -1 add up to 0. The way that we know that hydride is -1 for this one is generally because it's combined with a group 1 metal, sodium is a group 1 metal, or a group 2 metal. Okay? All the other cases it would be +1. C. C is not a compound, it's a polyatomic ion. How do we know it's a polyatomic ion? It's that charge they wrote up there. That tells you it's a polyatomic ion. There's more than one type of atom. There's carbon and oxygen. In fact, there's more than one atom. If there's more than one atom and it has a charge, by definition, it's a polyatomic ion. That's what polyatomic ion means. Now we got 4, right? So I'm going to do 1. I didn't make these very big, but that's okay. We'll make it work. So let's do the carbon and then the oxygens here. Oops, sorry. Too many. Let's get rid of one of those. There we go. Okay, so how do we do this one? Well, we come up and we say, is there a rule for carbon? No, there's no rule for carbon, but there is a rule for oxygen. Oxygen is -2 unless it's some weird thing like peroxide or superoxide. But normally oxygen's -2. So -2, -2, -2. What about the carbon? Now here's the tricky thing. In a compound, the charges add up to 0. In a polyatomic ion, they add up to the charge of the ion. So they wouldn't add up to 0 in this case. They would add up to -2. Polyatomic ion. Charges add up. In this case, -2, because the -2 is the charge that's shown there. So now we have to figure out what carbon is based on the idea that it's not going to add up to 0, it's going to add up to -2. So what do you have? You have -2, -2, -2. That's -6. Has got to equal, let's put it this way. I'm going to erase this. The -6 plus whatever it is for carbon has got to add up to -2. So just go through the algebra. If I add 6 to both sides, (6 and -6 is 0, so you have carbon on the left side. On the right side, you have -2 and +6, that's +4. So that means the carbon is, boy, that is really hard to draw +4 with a crayon in a circle that big. There we go. Is that better? +4. Check it. -2 plus 4 -2 -2, that adds up to -2, right? So there you go. We got it. So if someone said, what is the oxidation number of carbon in the carbonate ion? You would say +4. If they asked, what is the oxidation number of oxygen in the carbonate ion? You would say -2. Okay? One more. Let's see what this one more is. It is the N2O5. Oh, this one is relatively easy. I see what they're doing with this one, though. They're going to give you an oxidation number that's not a whole number. N2O5. There we go. All right, N2O5. So we have 5 oxygens and 2 nitrogens. Again, I'm making those too small. Boy, do I have enough? N2O4, N2O5. Wow, we got one more. Let me try to fit it in over here. Okay, so O, 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 N, N. Okay, N2O5. Doesn't matter where you put them. We're just trying to figure out what they are. Okay, so we come back to our rules. Oxygen, -2. So, -2, -2, -2, -2, -2. Rules for nitrogen? They're not in there. There's no rule for nitrogen in there, so we figure it out from the oxygen. That's the logic behind these. You find the elements that are in the table and write the numbers down, and then you figure out the ones that are not in the table from those numbers. Okay, so what's our negative charges? This is all adding up to -10, right? There's 5 of them, so 5 times -2, that's -10. So that means the nitrogens have to add up to +10. Right? Because this is a compound. There's no charge written, so that means the charges are 0. Okay? But keep in mind, there's 2 nitrogens. Okay? So if there's 2 nitrogens and they got to add up to +10, what do they got to be? Right? Just divide it by 2. You get +5. So +5, +5. Okay? So that's +10. So now, again, the question could be, what's the oxidation state of nitrogen? What's the oxidation number of nitrogen? It'd be +5. We report the oxidation number as one individual atom, not all together. So we wouldn't say it's +10. We would say it's +5. If we were asked what's the oxidation state of oxygen, we would say -2. Each one is -2. Now, it's an interesting assumption that they're all -2. Would it be possible that one's -1 and one's -3? Well, we're not going to deal with that kind of issue. We'll just say that they're all going to be the same. They're all going to be -2, just like the nitrogens will all be +5. So there it is, assigning oxidation numbers in redox chemistry. Practice those.